The next paper is going to be presented by three presenters, Clinton Char and Larry Wittek from Southern California Edison, and Gary Troya from Berkeley. Clinton is currently a project manager at Southern California Edison. He has 23 years of transmission and distribution engineering experience. Clinton serves on 3 ASCE technical committees and has authored 8 technical papers. Larry Wittek, also of SCE, has 17 years of transmission and distribution experience as both a lineman and foreman. He is currently a technical specialist with Southern California Edison's Transmission Engineering Department. Gary is currently an Implosive project manager at Berkeley. He has over 20 years of connected design and application experience for the electric power industry. He has authored several technical papers relating to connection technology. He is co-author of Connection Theory and Application and has been awarded 9 US patents. Please welcome Clinton, Larry, and Gary.
Thank you and good morning. The main part of our presentation here this morning is going to be actually on the testing program that we went through and developed for this. But to get everyone initiated and up to speed as to what it was that was tested, I'm just going to introduce the actual product itself so they have an idea as to what composes this and what makes this a little bit different than standard connection technology. The Implosive product is actually designed in a way that it actually ships with the energy, basically, in order to compress the product onto the conductor. It is a high compression process. It is not a fusing type of process that many people often associate with an Implosive product. It does have some unique design features associated with it. The materials that are used in this are substantially different than what would typically be used in a traditional tool and die type of system. And we have so much energy available to us in this wrapped formation that we're able to think outside the box, if you will, as far as what materials we use and how we go about the design process. In an installation aspect, it also brings out some areas where we can get some productivity increases. And one of the aspects here is that we see a triple bundle line actually being installed with splicing all at one time. Very simply put, the assemblies are all put together at the same time and all equal in how they're getting put together. The actual installation process takes, if we're talking about how long it takes to make the crimp, it's 1/10,000th of a second. And this is what the process looks like. This is what we all came here for, right? Oops. How do I get that? 5 minutes. Does make some noise. And with that, again, all 3 of the splices were done and ready to go. This is what the final product ended up looking like at the conclusion of the installation. Again, highly compressed down onto the conductor. We actually can see where the center core area is and how it's centered within the connection itself. So it gives us some immediate inspectability aspects associated with it. And these splices don't need any other preparation work associated with it either to clean off any sharp edges or things like that. So corona-free operation from there. Now, some of the aspects about what now these splicers are ready to do gives it some unique qualities, some unique properties. And it's those unique properties that gets people thinking outside the box. And I'm going to let Larry continue on and talk about how these unique features actually came into play for a decision to try to use in one of their projects.
Well, good morning, everybody. My voice is not that loud, so I need to take some. Again, my name is Larry Whitaker with Southern California Edison, and I'm going to go over some of the features of why we chose this technology for this TRTP project. And of course, some of them we got the rated for full tension. That was one main thing. And then the other issue is we had to be able to pull these through the travelers almost at full tension. We had to keep above the tree line. These were in the forest areas. And our conventional splices that we used we had to manually pass them through the travelers. So we had to qualify the Burndy Implosive splice to travel through the travelers at the rated tensions and at the rated angles that we were specifying. And of course we had quite a few environmental impacts that we had to overcome through this TRTP process. And like I said, this is for this segment here that we're going to be talking about. This is through the Angeles National Forest, which ranges from elevation from 1,000 to 6,000 feet, major canyons. And we had a lot of areas where we were not allowed to build access roads or roads for splicing locations. And again, as you can see up there, we had a string higher than normal tensions. Our tensions range from 8,000 to 10,000 pounds that we had to maintain through the pulling activity. Like I said, to keep that above the tree line. And as I said, we had the mountainous terrain. Part of TRTP was one of the largest transmission projects in Edison's history since the 1980s. It's roughly a little over 250 miles in length, and it consists of 11 segments. And within those 11 segments, there was sub-segments in those segments as well. For example, segment 11, we had a segment 11C, and so forth. So it actually more than 11 segments within that TRTP. What I'm going to do here is hand this over to Clint. He's going to go over the testing criteria that we used to qualify the Burndy Impo splice. You ready to go?
Oh, okay. Before I get started, Gary is Gary is in Atlanta, and he came out about a month ago to meet with Larry and I to put this presentation together. And halfway through our meeting, I had to go to another meeting, and they continued. Well, the result of that is they got 4 slides each, and I got 20. But they told me it's going to go by fast, so.
We have 17 minutes, Clay.
Okay, going back, Larry indicated that because of the sensitivity of the TRTP project and the rough terrain and mountainous area, that we wanted to try to consider using the Implosive splices for use on that project. And as what's that? Is that my heartbeat? I don't know. I am nervous. But anyway, what we needed to do is, when Edison brings in a new product, we always run it through a very extensive testing program. So what we decided to do is we decided to work with Burndy and Kinetrics to establish a testing program. So what we wanted to do is we basically wanted to validate the strain curves that the Implo provided to us. And basically, if you look here, there's 2 axes. This is strain curve that we got. This is line angle, and this is conductor tensions. So this chart basically tells us what line angles are acceptable for any given tensions. So what we wanted to do is we really wanted to validate this for the TRTP project. So what we did was we worked with Kinetrics, and we developed a 2-phase test program. The first program would be to test the line angles. So this is the setup that we use. We had we had a traveler here, and we had, I guess, a load cell here and a tensioner here. And what we did was we would rotate this, and this would be the splice. So we would rotate the splice over the traveler at set line angles at this point here. Now this was the implosive splice. These splices here were done by compression. So what we did on the program is we established 3 different line angles we wanted to test. We tested, I think, at 30 degrees, 40 degrees, and 50 degrees. And these are all line angles that were realistic line angles on the TRTV project. This is the lab view that we had. This is the traveler here. We had a tensioner on one end and a load cell on the other end. And what we would do is we would just pull this back and forth over the traveler to see how it would perform. So this should be a video of the closest splice going over the traveler. You can tell that when it goes over the traveler, it kind of hangs up for a little while until enough tension pulls it over. And we were really worried about this area here where the conductor would kink, because you have a very rigid body here going over a circular traveler, and we were afraid that it would cause stresses on the conductor at the mouth. So what we did next is, once we ran all the implosive splices over the traveler, we decided to put tension on it. Because what we wanted to do is we wanted to see whether there was any degradation in the conductor after going over the traveler. And the way that we would do that is to see, mechanically we would test it for strength to make sure that it maintained somewhere near the rated breaking strength of the conductor. And we also had a electrical test which we ran, a resistivity test. And we measured the resistivity across the splice before and after. And if the resistivity of the after was higher than before, then there might be some internal damage to the strand. So we did both of those tests. So in this one here, it's a typical tensile test. We put the splice here, and we just pulled the ends. So this is the setup. This is the compression end. The splice is here, and the other compression dead end is on the other side. This is a video of the test. We're just concentrating on this end, and about 10 seconds until it breaks. You'll notice that the brake was on the dead end. As you can see that there is a bird cage here. So there are several pass-fail criteria that we established. The first one is we wanted to make sure that the splices were straight when they went through the travelers. So the first pass-fail criteria was that there was no bending of the splices after passing through the travelers. And you can see Larry here, he's measuring with his ruler, I guess, to make sure that it's straight. The second pass-fail criteria was that there was no damage to the conductor. So what we did is after every time we went over the traveler, we actually measured, or we kind of investigated the mouth of the splice to make sure that there was no conductor damage. We did see, as you go higher, to the higher angles, we did see that the conductors were flattened, the strands were flattened. But in the tensile test that we ran, it really showed that there was really no degradation in the strength. And the third one was the tensile test. The criteria that we used was that we wanted to make sure that after passing over the traveler, that the conductor had 95% of the rated tensile strength per ANSI standard. So these are some of our results. We tested 1590 ACSR and Bluebird 2156 ACSR. You can see that we have the samples here. We show you the line angles here, 30, 40, and 50. And this is the rated tensile strength for the lapwing and then the Bluebird. You notice that we set the criteria at 95%, but we did have some that broke below 90. And when we looked at that, those actually broke on the dead end side. So we can probably conclude that the tensile strength of the splice would be higher than 90. That still didn't meet our 95% criteria though. But then we looked at the actual usage of the conductor. And typically when we use a conductor, we want to make sure that the maximum tension in the conductor is 50% less than the rated tensile strength. So if you consider that, 90% is still gives us a lot of factor of safety in the conductor. So based on that and where it broke, we decided that passed also our criteria. So what we did next is we actually took the Burndy strain charts and we actually plotted where our test results would land on the strain charts. And you notice that a lot of times our test results exceeded the Burndy strain charts, which was good. That's what we wanted. Because if it fell below, then we would be a little bit worried in that, we wouldn't know what we would get if we installed the conductor based on the Burndy chart. But because they were exceeded, we had a good confidence that we could use the charts. And I think the reason why it exceeded is because there's some factor of safety that's built into the Burndy charts. And if you look at the way we did it, we actually did an ultimate strength design where we just took it to failure. So this gave us confidence that we could use the Burndy charts in our TRTB project. And as I indicated earlier, when we looked at the results, a lot of the failures that we had was on the compression side. Again, this is what we talked about earlier. We did a resistivity test before and after, and we found out that there was no degradation in the resistivity. Well, there was no difference in the resistivity, so that means that there was really no internal degradation of the conductor. We also decided to dissect the splice because we wanted to see how good a splice it would be, and it's a very, very good splice. If you look here, this is an end view. You can tell that this is actually the splice here. You can see the conductor here, and that's the steel core. It's very, very homogeneous. If you look here, this is a side splice here, a slight dissection. This is the conductor. This is the splice. This is the conductor in here, and then this is the steel core. You can tell it's very homogeneous. There's very, very minimal air gaps, very, very few voids. Well, actually nothing that we could see with the naked eye. So it gave us confidence that it was very uniform, and it gave us confidence that it was a really good splice that we could use on the project. As Larry said, the project is about 90% under construction. It was probably done. We have about 10% more, and this is what it looks like. It's been through very rough territory. So in conclusion, we found out that during the test, the Implosive splices tested very consistently. They made very good connections. We didn't really have any degradation in the splice when we put it through Traveler. We validated strain charts, and we found out that by testing the splices to the Travelers, that it really meets the inflow strain charts and the parameters that we decided to establish for the project. From a project perspective, we ensured that the line angles that we pulled through were in accordance to the inflow charts. We wanted to make sure that the diameter Traveler was equal to or greater than the specified, inflow recommendations. And we really followed the installation of the splice according to the manufacturer's recommendations. So this was very successful on the Edison project. So, thank you. Any questions? And oh, we finished with 7 minutes. I guess you guys are right. My part would be fast. So, is there any questions?
Who's it? I don't know which one of you guys be most able to answer this question. What about the I know the government changed the classification of the inflows to from a 1.2 class explosive to 1.4 or vice versa. That's been a problem for us, for my company, TBA, as far as transportation and storage of them. Did you have any problems with that?
Well, yeah, for Southern California Edison, we are not as a utility. We are now not allowed to handle the implosive splices nor store the implosive splices. So we had a contractor, our contractor that was doing the job. They handled all the storing and the transportation of all the implosive splices, and also we had to have a certified blaster on site for this as well. The for Southern California Edison, the utility, we don't have a certified blaster, we're not qualified. So we have to reach out to somebody who was qualified to store it and detonate. So hopefully that answers the
Actually,
question.
yeah,
Okay.
we actually had to have some people certified.
Yeah.
Basically, we just stopped using it.
Yeah.
It's really good, I hate to see it out of our toolbox.
Yeah, no, it's a good tool to have in the toolbox, that is for sure.
I think there was a question.
It was-
Kind of on the same line, being that you're in a forested area, what other precautions did you have to provide so as to not start a wildfire or have something like that happen?
Well, in Los Angeles, as you know, we have fire days, and certainly we are not going to install one of these during our fire days. We have I think the contractor that we had on board did have their own fire crew, and they were certainly stationed at the site during the installation. We also had to warn, I guess, any residents that were nearby. I think it was determined that any residents within about a half a mile, we would warn them of when we would do an installation. But other than taking those two precautions, we really haven't had any problems with the installation.
Did you guys consider dynamic load and fatigue in your testing?
Probably not. No, we didn't really consider that because primarily when we install the conductors, would be underground, so there would really be no dynamic load on the towers. And once they're installed, then we would pull them onto the towers. So the towers wouldn't see any dynamic or shock loads at all.
Any other questions? Not? Thank you.